All right. So polychromatic is defined as a compound dye or mixture of dyes that contain components of different colors. Um, so if you just remember that poly means many and chromatic means color, then you have your definition. So um, compound dyes are mixtures of different dyes. Okay. So a classic example is the Giemsa stain. The Giemsa stain has multiple different dyes that are different colors that are mixed into one solution. So when you put it on your slide, those different dyes have the affinity and seek out different components in your tissue, okay? And will dye different components within your tissue. So there's sort of all these little guys in this one solution going, hey, dump me on the solution, but I'm going to go after this target. I'm going to go, the other one's going to go after that target, and another one's going to go after this target. Okay. That's polychromatic. Um, Really, you're going to see polychromatic done, a handful of times. Yeah, but it's in the Giemsa stain, its whole purpose is to seek out and differentiate different hematopoietic tissue. So, what is hematopoietic? Hematopoietic tissues are tissues that are composed of all different types of cells that stain differently. So, um, classic example, bone marrow. Okay. Yeah. So we have stem cells that are self-renewal or production cells. We have progenitor cells, which are progressive generators, right? Yeah, generating energy, generating all kinds of reactionary chemical processes. Then we have precursor cells, and these cells are specific to a certain lineage, meaning here I I'm going to be a red blood cell, but I'm not quite a red blood cell yet. I'm still sort of waiting in the background until it's my turn to become a, red blood cell. And then we have functional red blood cells. So, uh, again, when we talk about hematopoietic, we're talking about blood smears and we're talking about bone marrows. Somebody has bone, and I told that person, yeah, to start diving into bone marrow. Um, Cases, because when we get a bone marrow case, we do not just get the biopsy. We also get what's called an aspirate, and we get multiple different smears that happen, yeah, for us to stain. So that person who has bone, know that this is sort of what you're going after. So the Giemsa stain. The Giemsa stain is one that we use on hematopoietic tissues. So uh, let's see, when we start talking about special stains, not only do you need to know the steps to the special stain itself, but you also need to know the function of each one of those steps. Okay. So and it's fixative. Okay. Yeah, and it's quality control. And it's quality control. What that means is that we have this case, this patient, and we have to prove to the pathologist that all of the special stains that we ran on this case are proven to have worked. Okay. And so our proof is what's called a control. A control is a specific tissue type that we know works to prove that that case is valid. So remember that when we're special staining, we may run a special stain that may be negative, okay? Meaning that it's not going to be, positive for that tag that we're going after, for that element or that component that we're trying to stain. So we have to provide the pathologist with a slide that's ran identical with that patient slide, proving they both went through the same process. And this one is positive, therefore, which is our control. Therefore, we know that this stain worked correctly even if it is negative and the target doesn't light up. Does that make sense to everybody?
Yes.
Anybody confused about that? Because controls are very important.
Can you please repeat that again?
Yes. Andrew, did you have a question?
Yeah, so you said a separate slide. Do we do that on the same slide or the two different slides?
Well, there's a whole lecture about controls that's coming up today, and it can be done either way. You can
Okay.
put a control on top of the slide and then the patient on the bottom of the slide and run that slide that way. Or you can have patient slide and control slide and run them identically through the stain process. Yeah, and do it that way, proving your case.
Okay.
Okay.
Makes
All
sense,
right.
yeah.
So, what is a control? A control is a known tissue type. Okay. And it can be a case type. It can be a patient that we've previously diagnosed with tuberculosis that we know has TB in it. It can be a kidney that we know has basement membranes in it. And then, oh, we've got this patient over here that maybe we're looking for kidney disease on. And we know that this slide here will demonstrate that disease, okay? But we're testing this patient, which may or may not have that disease, okay? So we take both of these slides and we run them together identically through the stain process. And in the end, this one will be positive because it's a known case that we know will demonstrate that disease. But this one's the patient, right, that we're testing that may be positive or it may be negative, okay? But by having this control, we can prove to the pathologist that our stain actually worked. Does that make sense? Does that help, Angel?
Yes.
Okay. Katrina, did you have a question?
Yeah, so it's basically like confirming your case
Yeah,
and
it
it's
is.
about
It's
oh,
confirming that it's confirming that the test that you ran was ran correctly.
oh okay, thank you.
Uh-huh. Okay, so back to our Giemsa. The preferred fixative for Giemsa is NBF, neutral buffered formalin. It could be Zankers or it could be B5. But again, what's wrong with this? Mercury components, right? So really we prefer NBF. It's a paraffin embedded tissue. Yeah, it's cut at 4 to 5 microns. Its quality control, okay, yeah, is spleen, because we know spleen is a hematopoietic tissue. So there are some reagents that are intermixed in here. There's Jenner's solution, there's Giemsa solution, and there's acetic acid. So what is your Jenner solution? Your Jenner solution is a stock solution that's made into a working solution. So what does that mean? A stock solution is a solution that is pre-made, that hangs around in its bottle, but it's not a usable thing until it is added to other components. Okay, so that when you add water to it, that is a working solution, which means now that solution is able to go onto the tissue. Okay. So stocks are just, they're pre-made, they're hanging out, waiting to be made into this solution that we can use on the slide. So your stock solution is 1 gram of Jenner dye, and that's a powdered dye, plus 400 mils of methyl alcohol. Then you take this stock solution and you take 25 mils of that stock solution and you add 25 mils of distilled water, and now you can put it onto your slide. Then your Giemsa solution. And just so you know, not everything has a stock. Stocks are made so that we can keep it around longer, to utilize it longer. Working solutions have less of a shelf life than stock solutions do. Okay. So your Giemsa stock solution is 1 gram of Giemsa dye, and that's a powdered dye, plus 66 mils of glycerin, plus 66 mils of methyl alcohol. Then you take this stock solution and you put 50 drops of this stock into a bottle, and you add 50 mils of distilled water, and now you can use it on your slide. Now, working solutions can be held. Okay, some working solutions can be held because they have a longer shelf life. But there are working solutions that have a shelf life, of a few hours, to a day. And then there are working solutions that can be held and used, for weeks. Yeah, it just depends on that particular dye that we're using. So in this instance, your Giemsa solution has to be made and prepared fresh. Your working Giemsa solution has to be made fresh. You're going to see Carson say, must be made fresh. Yeah, but she doesn't necessarily give you a time frame of what that means. Okay. Having been around the block, I sort of know what that means now. So in this particular instance, that working Giemsa, you've got a couple hours, 4 or 5 hours, to actually use that working solution. Then you have a 1% acetic acid. So this is 1 mil of glacial acetic acid to 99 mils of distilled water. So your protocol. You are, if you are using a paraffin block, okay, you're going to depair and hydrate to water. If you're doing a slide, a smear, like you're going to do in your cytology, you're just going to start, okay? So if you have used Zankers or B5, and you can revisit this, yeah, but if you've used Zankers or B5, we know that there's a mercury component to that, and you have to remove that mercury pigment, okay? Then we're going to go into methyl alcohol. And yeah, this is 2 to 3 changes, okay? And that's just introducing that alcoholic environment. Then you're going to go into your Jenner solution, and you do this methyl alcohol, yeah, if you're doing a blood smear, yeah, or a cytology. If you are doing a paraffin block, you've already depaired and hydrated, but you're not going to go all the way to water, okay? You're going to depair, and you're going to go to 95, yeah, but then you're going to drop it back into 100% alcohol, methyl alcohol, yeah, for 2 to 3 changes. Now, does it have to be methyl alcohol? No, any alcohol will work. So yeah, even though Carson says methyl alcohol, which you're going to have to sort of reiterate that on your certification exam, but the truth to the matter is any alcohol will work, including our denatured 100% alcohol. So you're going to go into 2 to 3 changes, and that's going to introduce that alcoholic environment back to the tissue or the smear. Then you're going to go into your Jenner solution. Your Jenner solution is your nuclear stain, and it's going to stain blue. Then you're going to go into your Giemsa solution. So we're talking hematopoietic here. Yeah, and we're talking polychromatic. So it's going to stain your cytoplasm and your leukocytes. Yeah, but your leukocytes are going to stain different shades of pink, gray, and blue, dependent upon what state they are in development. Okay. Then you're going to distill water wash. Yeah. And then you're going to differentiate back out your hematoxylin and your Giemsa with a 1% acetic acid. Then you're going to distilled water wash, and then you're going to DCM. Now, at this 1% acetic acid, yeah, you need to check it microscopically. So how do you do that? You need to get used to what's called a toggle. Yeah, and so you take your, you take your slide and you put it into the acetic acid, give it a couple dips in the acetic acid. You pull it out, you dip it into your water to stop that differentiation from happening. And then you pull your slide, you wipe the back of it, and you put it underneath the microscope, and you look at it microscopically to see if you've actually got the right components stained at the right level. If you do not, then you go back into your acetic acid, just a little bit, and then you go into your distilled water, and you check it microscopically again, okay? From here to here is your toggle. Now, I caution you, when you're new, you tend to look too long at that slide microscopically, okay? So have your distilled water sitting right there next to your microscope, and you pull it out, you wipe the back, you stick it underneath the microscope. Don't let it dry out. So pull it, dip it in your water, wipe the back, stick it back in. Pull it, dip it in your water, wipe the back, stick it back in. Because again, if you dry it out, you're gonna get corn flaking. Okay, so keep your water handy. So your results microscopically, what should it look like? Your nuclei are going to be blue. Your cytoplasm are going to be shades of pink, gray, or blue, dependent on that cell type, okay, that cell lineage. If you happen to have any type of bacteria in there, which happens in blood slides, they can, have some blood disease process happening. Yeah, even in bone marrow slides. Okay. But if that patient just happens to have bacteria in there, it's going to turn up blue. You got to make that working solution, right, just before you use it. And the pH of your solutions should be somewhere between 6.4-ish. And this is what it looks like. So you can see the different cell lineages. Your nuclei are purple. This one's sort of light gray. This one's dark blue and pink. So depending upon where that cell is in lineage, it's going to pick up different colors because of that polychromatic staining. Then we have what's called the Fuelgen. The Fuelgen that's a German man. So it's Fuelgen. Yeah, so its key sort of reagents are acids and that are used to hydrolyze the tissue, and Schiff's reagent. So our preferred fixative is formalin for paraffin embedded tissues. We can never ever use Bowens on this particular stain. We don't want to fix in Bowens because the picric acid in Bowens will interfere with that hydrolysis. So our reagents, we have a 1 normal hydrochloric acid that Carson's going to tell you to heat. Okay, I'm going to tell you otherwise. And it's been, because really we don't want to heat hydrochloric acid, right? It's dangerous. Yeah, so it's been proven that you can use a 5 normal hydrochloric acid at room temperature and it works just the same as a heated 1 normal hydrochloric acid. So yeah, if you're ever running this stain, do it with a 5 normal hydrochloric. Now, this is not normally done anymore because this particular stain has been replaced with immunohistochemistry, with the development of immunohistochemistry. However, it is still in Carson, so you're going to hear me say this a lot. It's in Carson, so it can show up on your certification exam. So you need to know it. Okay. So our reagents, you're going to have that hydrochloric acid. You're going to have Schiff's reagent. You're going to have a sulfurous acid. And we're going to be demonstrating just the DNA, not the RNA or other components. Oops. So your protocol, you're going to depair and hydrate to water. Then you're going to rinse it in a 1 normal hydrochloric acid. This is still true. Yeah, so you're going to rinse it in a 1 normal. Yeah, this is going to start that hydrolysis of DNA. And what that means is we're creating an aldehyde. Okay, that's the definition of this hydrolysis, is we're actually molecularly creating an extra aldehyde on the molecule so that it can be stained on the DNA molecule so that it can be stained with shifts. Okay, so we're creating another aldehyde. Yum. Now, Carson's going to tell you, you have to go into a 1-normal hydrochloric acid. Then you have to go into a heated 1-normal acetic acid that has been heated to 60 degrees Celsius. That's going to continue that hydrolysis. Then you're going to go into a quick dip of 1-normal hydrochloric acid that is cold, sort of room temperature, just to bring down the temperature from heating it in this acid. And it's going to stabilize it back down to room temperature. When you look at all of this can be eliminated by just simply having a 5-normal hydrochloric acid and putting your slide in there for a little bit longer. Okay. All right. So once you've created that aldehyde through hydrolysis, then you're going to distill water wash. And that's going to remove the excess hydrochloric acid, and it's going to stop that hydrolysis from happening. It's going to stop that creation of that extra aldehyde. Then you're going to go into shifts. Schiff's reagent is a sort of wheat color to pink. Yeah, it's your DNA stain. Yeah, Schiff's reagent lives in the refrigerator. And when you need to use Schiff's, you need to pull it from the refrigerator, get yourself a transfer pipette, a plastic pipette, pull out what you need, put it in a little beaker, bring it to room temperature, okay, before you use it. And then the bottle of Schiff's needs to go back into the refrigerator as soon as possible. If you leave that whole bottle of Schiff's out on the counter, it's going to react with the sunlight and the air. And then that whole bottle, because it's already reacted, that whole bottle of Schiff's is no longer usable. Okay, so you take what you want out of it and you put it back in the fridge. Now that Schiff's reagent is going to stain your DNA, and even more specifically, it's going to stain the aldehyde group that you just created from the hydrolysis step up here. Then you're going to water wash. Coming out of Schiff's, you're going to water wash. And this is what's called a development step. And so with Schiff's, you may not see, sometimes you will, sometimes you won't, depending upon what it is that you're staining, if it's a large target or a small target. So you may not see any of that pink color, any of that pink dye on your slide when you come out of Schiff's. It's not until you hit it with water where that pink color is going to rise. So you give it this nice long water wash after the Schiff's, and that's going to develop up that rose color, that rose pink color to come to the surface. Okay. This is true for your hands, ladies and gentlemen. You grab that Schiff's bottle out of the refrigerator, and you're not wearing a glove, and you won't even know it's there, until you go and wash your hands, and then all of a sudden your hands are pink. If that happens to you in the kitchen, underneath the sink, is some special soap, that will help remove that pink color. Okay. It's even more embarrassing when you don't know that you have it on your hands and you like scratch your forehead. And then you take a shower later on and all of a sudden you have this pink blob on your forehead. Okay. So, Yeah, use gloves when you use shifts. You should have gloves on throughout your staining processes anyway, including your goggles, because you need to wear your goggles whenever there's the ability for splash factor. Okay. So side note, that's just side note. Yeah. All right. So we've brought our rose color to the surface by developing it. Okay. That's the term. And you need to know that. And then I personally don't like this. Yeah. I never used this because I have an opinion about it. But then you can hit it with the sulfurous acid. And this is going to stop that shifts reaction. And it's going to remove any unbound shifts. Okay. And when I say unbound shifts, what does that mean? Any non-specific staining. Okay. Then you're going to water wash. And that is going to completely remove any unbound shifts or non-specific staining and wash it away. Now, here's my opinion on that. It's my opinion that if you initially worked up your stain appropriately in the first place, you would not have to worry about any non-specific staining, making this step irrelevant. Okay, my opinion. So, yeah, then you're going to counter. So you're going to counter usually with a light green, because that's the DNA is going to be that rose color. Okay. So opposite color wheel, you're going to counter, and actually it's a background of light green. You got to really be careful, with the light green with this, because we are staining DNA. It's itty bitty teeny weeny, right? It's going to be really, really easy to overlay your DNA. In fact, some pathologists will ask you to not counter at all, leaving your DNA the only thing that's tagged on the slide, because they don't want to take the chance of that overlay. Then you're going to dehydrate, clear, and mount. So your results, your DNA is going to be rose to a reddish purple. And I say that reddish purple because that's that overlay color that can exist. Okay. And then everything else you countered is going to be light green. This is what it looks like. So you have your DNA inside that's stained pink, and then if you have countered, you have your light green staining everything else. Then we have the methyl green pyranine. So this guy stains both DNA and RNA. Its fixative is NBF. It's used on paraffin embedded tissue. And in your control, you need
Melissa.
in your control, you have to have plasma cells. Well, they're everywhere. So they need to be present. So basically you can use just about anything. Or a blood smear is really good with that. So your reagents, you need to have an acetate buffer, and that acetate buffer is two different stock solutions. It's an A and a B. You add it together, and then you adjust the pH with either an acetic acid or with a sodium hydroxide, to get that pH to a 4.2. Then you have your methyl green pyranine staining solution. Yeah, you can look in Carson for that. We'll go over that in just a second as well. Now, it takes several hours, if not days, to prepare the methyl green pyranine solution itself. So if you are the last guy who used up the last of the methyl green pyranine and didn't begin making it again, and this stain gets ordered again, you're going to create a delay in patient results. Now, another thing about this is that your dye sources, when you order the dyes, they cannot be substituted for a lower or less pure dye. They have to be pure, right? And again, this is one of those stains that has been replaced by immunohistochemistry. All right, so your acetate buffer. You have a solution A and a solution B. They are both molar solutions. So your solution A is 2.3 mils of glacial acetic acid in 197.7 mils of distilled water. Your solution B is 272 grams of sodium acetate trihydride in 100 mils of distilled water. Now, molar solutions deal with the molecular weight of a dissolved particle. And in my book, Carson explains that on page 98. If you want to look it up, you'll be close. Okay. So then we take those two, solution A and solution B, and we mix them together to make our working solution. So our working solution is 150 mils of solution A to 50 mils of solution B. Then you adjust to that 4.2 pH. Your methyl green solution. So you have an acetate buffer working solution, which is 200 mils and with 1 gram of methyl green dye. Again, there's prep for this. In my book, it's on 128. You'll be close if you look it up. But you have to mix this in the hood because you are going to be using chloroform, and there's some more info coming your way. And then this solution has to stand overnight to evaporate the chloroform out of this solution. So this is a procedure that's called the chloroform extraction procedure. So what you do is you take equal quantities of the stain that you just made here and chloroform, okay? And you put it in what's called a separating funnel. So a separating funnel is also known as a carboy type situation. It's a container that, it's containers like this, or the funnel is like this. And then there's a release on the bottom of it, a lever that you can like pour stuff out of. So what will happen is you're going to mix the chloroform and you're going to mix the stain, and then you're going to shake it, and you're going to make sure that it's all mixed really well together. Okay. Then you're just going to let it sit. And as it sits, the chloroform is going to drop to the bottom of the container. And then, you're going to go back the next day, yeah, and you're going to open up that little spigot on the bottom and you're going to drain out that chloroform. That chloroform, when it comes down to the bottom, it's going to have a little tinge of stain to it, and that's okay. But then, you're going to drain out that chloroform, yeah, and then you're going to let it sit again. Shake it, let it sit. And you continue to do this until there is no more separation of chloroform coming out of that stain. So virtually what's happening is the chloroform is attaching to the impurities within this dye component, and it makes it heavy, so it drops down, and then we can sort of filter it out by releasing that tap and taking that chloroform out. So our protocol, yeah, we are going to depair and hydrate. Yeah, then we're going to go into the methyl green pyranine solution. This methyl green, yeah, will stain the DNA and the RNA. So that makes it polychromatic, right? So the DNA is going to stain green, and the pyranine, the methyl green, is going to stain the DNA green. And then the pyranine is a red color, so it's going to stain your RNA red. Then you're going to distill water wash, and that's just going to rinse off all that excess stain that's remaining on your slide. Now, this is one of those stains that you are going to allow to dry out. There's like 4 or 5 stains that we actually do dry out. So you're going to blot it on filter paper. And when I say blot it, I do not mean if my hand is my slide and this is my filter paper, I do not mean go like this, okay? What you want to do is lay your filter paper down on the table, and then you take your slide and you just drop your slide straight down. Yeah, and you just allow it to sit there, yeah, and allow the filter paper to absorb the solution and dry that slide out. Then when you're ready, you put your finger on the tip of the slide and you stand it straight back up. Now, the reason I say that is because if you're doing this, you're actually damaging the cells and or the section that's on the slide, okay? Yeah, so once you have removed all the water, now notice that in this procedure, we do not dehydrate. We do not go through alcohols. So this is why we have to sort of dry this slide out, because we don't want water to get into our xylenes, and we don't want water remaining on the slide, because then it's going to interfere with that stain microscopically. So we could still have to differentiate it. So we're going to go into acetone, and this is very quick. So it's literally, my slide is dried. We got a Copeland jar of acetone. I'm just going to go bloop, bloop, and I'm out. Okay. Then you're going to go into an acetone xylene mixture. So that initial dip in acetone is differentiating. Then this acetone xylene, it's a 50-50 mix. You're still going to have a little bit of differentiation from that acetone. But we're actually starting to clear, with this xylene. Now remember that acetone is universal, so not only is it going to continue to diff, but it's also starting that dehydration process. We are not dehydrating with alcohols because alcohols will pull your methyl green. So From here, we're going to go into straight xylene and 2 changes of it to make sure that we have stopped the differentiation and we have cleared our slide. Then we're going to go into a last xylene. This is a safety net. It's a 3rd change. And we're just assuring that there is no acetone left on that slide. So we're going to drop our slide in here and let it stand for a while. It's not going to hurt it to sit there for, 3 minutes, to sit there until the end of the day. Okay. Then you're going to mount it. So our DNA is going to be green-blue. Our RNA is going to be red. Our goblet cells are going to be this sort of light minty green, as Carson calls it. Plasma cells will look much like your red blood cells. They're going to be that bright, intense red color. And then your nuclei are going to be green to blue. And this is what it looks like. So you can see the reactions that are having. Your methyl green pyranine will stain your RNA rich, and your dividing cells pink. Okay. This is another one. So the RNA, notably in the plasma cells here, and if there's any acid mucins, they that happen to be there, okay. It's not our target, they just happen to be in that particular section. Yeah, they are going to stain this bright shifts magenta color. And then the DNA is this green to purplish color, sort of out here, and in here. Questions? Yeah, Angel.
If we use the 5 normal hydraulic acid, is it gonna be the same protocol? Since in the first protocol of the 1N, it says that we will heat it and then we will cool it down to go back to the room temperature. Since 5N is not heated, so we're just gonna start with after the cold.
You don't even start with the 1 normal. You just go straight into cold 5 normal. Okay. So that 1 normal cold to hot, 1 normal to, all 3 of those steps, the cold, the hot, the room temperature, all 3 of those hydrochlorics are eliminated by using 1 change of 5 normal.
Okay, thank you.
Okay. Okay. Other questions? Netton?